Okay folks, if you've been following along, it's finally time to derive the formal Kalman filter. Okay? So in the past we've gone over linear least squares, we've gone over sequential least squares, we've gone over some optimal estimation techniques, some model reference adaptive controllers, and so now it's time to derive the Kalman filter. And what the Kalman filter is, it's a way to, it's a sequential nonlinear, if you extend the state, so it's a sequential linear observer that tries to integrate your model dynamics, or the estimate of your model dynamics, and then use the measurement and the estimate of the covariance to do a least squares regression on your measurements to converge to your actual system state. And so it's a blend of a lot of things put together. So first what we do is we assume we have some truth dynamics fx, and this is the linear Kalman filter. So there's an extended state Kalman filter, EKF, which is usually employed on a lot of drones and things like that. And if you look in the hardware, you'll see EKF everywhere, or AHRS everywhere, and EKF stands for extended Kalman filter. This is just the linear one. So I'm assuming f is linear here. I'm going to have a g times a u, and I'm also going to have some model noise. And so what this means is that the system is going to get hit with some weird model noise where even if I wrote it down analytically, it would still get kind of jumbled around. Okay? Remember, I'm going to assume that the expectation of my model noise is equal to some matrix Q. Okay? I then assume that I've got model dynamics where I get to run on the system itself, where I may have done some parameter estimation, or perhaps I have a self-tuning controller on board that estimates the model dynamics. Those things can all operate in tandem, but basically you assume I've got some f tilde x tilde, g tilde u, and remember u is deterministic, right? So if you were putting control system hardware on a drone and you were sending a command to a system, that is a deterministic signal. How it propagates through it, or where the error comes from, is through G and W as well. This is going to have initial conditions x naught, which is hopefully going to be equal to your initial measurement. If not, if you can't get an initial measurement, then you're just going to have to do a guess. Okay? Every time, now if you took this by itself, right, and I took my initial measurement, x naught, and that was obviously different than my true state, x naught, my dynamics of my system would, say, do this. First of all, I would be off by a little bit, and my dynamics would be off. So eventually, I might match a little bit, but eventually I'm going to be off by quite a bit here, okay? And so what I need to do is I need to hope that at some point I'm going to get some state update, state measurement, where I measure, I'm going to call it yk, where I measure yk. And what I want to do is, remember this x naught, this is x tilde naught now. And my state here, I'm going to call this x tilde k minus. What's going to happen is I'm going to get a new measurement, and hopefully what's going to happen is I'm going to get what my actual state is plus some noise. So I'm going to assume that I'm going to get y bar k is h xk plus some noise, and I'm going to assume, remember, that the expectation of my noise vector is r. So I'm assuming that the measurement that I get is my actual state plus a little bit of noise. And this is going to be my x bar k. What I'm going to do is I'm going to do a least squares update. Boom, and I'm going to update to x tilde k plus, and then continue the propagation. So basically what that means is I need this, my model dynamics, I need my initial conditions, I also need a state update, so I need xk plus is going to be xk minus, And if you remember from like the complementary filter that we did in the sequential linear least squares, I'm going to have a Kalman gain matrix times my measurement minus hxk tilde minus. Okay? And that is going to be my update equation. And so what I need to do is I need to update my state every time I get a measurement. Now the thing is that I need to also add something which is called covariance propagation. So I need to define my covariance P, which is the expectation of my error, where x hat, again, like I said, is my error, and I need to make sure I got my signs right, is my model minus my actual state. Now if I want to grab P dot, that's going to be the expectation of x hat dot transpose minus, or sorry, plus x hat, I gotta do chain rule, x hat dot transpose, and x hat dot is x tilde dot, which is this equation, minus x dot, which is this equation. And if you do all the math and shake everything out, what you actually end up getting is you get P dot is f tilde P plus Pf tilde plus MQN. MQN, and I think there's a transpose. And so again, remember Q is the estimate of your model noise, and M is sort of the matrix that multiplies in. So if you're lucky, M is just identity, and this just propagates to P. So what are your initial conditions of P? Well, remember, P is the expectation of x hat transpose. So P naught is the expectation of your initial error estimate transposed. So if you're lucky, if you have a drone sitting on the ground, you can let the algorithm run a little bit, and your initial covariance will hopefully be very small before you finally take off. If you just like throw the drone out of the gate and have it hit and turn on, your P naught is probably going to be pretty large because your initial error estimate is probably going to be pretty large. Okay? So that will propagate the covariance. This will propagate the model dynamics. This will update your state. You also need to update your covariance. And so if you look at these equations, right, I can write these out, and I can say that pk minus is the expectation of x hat k minus transpose, and then pk plus is the expectation of xk hat plus x hat plus transpose k. And if you look at x hat k, that's x tilde at tk minus x at tk, and you can use this equation and these two equations and substitute them in, because you have an xk tilde minus and an xk tilde plus, and you can shake all of this out, and what you end up getting is pk plus is equal to the identity matrix minus kk, so the kth iteration of the Kalman gain matrix, times h pk minus. Okay? And so that is your update for your covariance. So again, let's reiterate. You integrate your model dynamics, you integrate your covariance. Whenever you get a measurement, you update your state and you update your covariance, and then you keep integrating. So the question, of course, is how do you choose your Kalman gain matrix? Well, remember I was saying that your Kalman gain matrix is a linear least squares. So what we need to do is we need to develop a cost function and then minimize that. The cost function that we're going to use is P. Because x is my estimate minus my actual, I want to minimize the expectation of my error, or basically minimize P. And it turns out if you minimize P, if you minimize the trace of P, you also minimize P itself. And so what we're going to do is we're going to create, let me take a picture of this, and then we're going to create a cost function. Okay, so what we're going to do is we're going to say J is the trace of PK, okay? And then what I want to do is I want to compute del J del PK and set that equal to 0 and solve for K of K. And it turns out that there are people smarter than me, maybe not smarter than me, maybe have more time. They derive this for us using a lot of linear algebra rules, and they get that the Kalman gain matrix that satisfies this minimization is PK minus H transpose HPKH minus transpose plus R inverse. And remember, R is the covariance estimate of your noise of your measurement. And that there, my friends, is the optimal Kalman gain matrix. So you integrate your model dynamics, you integrate your covariance. At a state update, you compute your Kalman gain matrix, you update your covariance, you update your state, and then you continue integration until you get a new update. And according to the observer rules and complementary filter rules and least squares estimation, at the end of the day, your x tilde should converge to your true state x. Okay? And if you watched a couple videos on this in the past, you'll see where I rigorously derived that. But that is the Kalman filter in a nutshell. If you have any other questions, if you'd like me to do extended state Kalman filters or anything like that, post a note in the comments and I will consider it. This is officially the last lecture that I'm going to do for nonlinear control. So if you're in my class and you're watching this video, it's been a pleasure, and hopefully I'll be able to see you again.